Hello, everyone. My name is Drgona. I'm a data scientist at Pacific Northwest National Laboratory. In today's video, I will introduce you to NeuroMANCER, a new scientific machine learning library written in Pytorch. After this video, you will learn what is NeuroMANCER, why we developed NeuroMANCER, what is scientific machine learning, what can NeuroMANCER do for you, how do you install NeuroMANCER, and who is behind NeuroMANCER. First, NeuroMANCER is an acronym that stands for Neural Modules with Adaptive Nonlinear Constraints and Efficient Regularizations. Second, NeuroMANCER is a reference to a fantastic science fiction book written by William Gibson with the same name. But most importantly, NeuroMANCER is open source scientific machine learning library hosted on GitHub. NeuroMANCER is allowing you to formulate and solve parametric constraint optimization problems, physics-informed system identification, and parametric optimal control problems by using differentiable programming to combine modern data-driven methods with optimization modeling language in a coherent algorithmic and software framework. Much of our philosophy is borrowed from Pytorch that is focused on research, rapid prototyping, and streamlined deployment. Strong emphasis is given to extensibility and interoperability with Pytorch ecosystem. We want the user to be able to quickly adapt our examples and tools to new application domains. The core features of NeuroMANCER is a comprehensive library of differentiable modules that include custom activation functions, constraint weights, structured deep learning architectures. Examples include graph neural networks, neural differential equations, closed-loop dynamic systems, or implicit layers with iterative solvers, and more. Our front-end user experience is defined on minimalistic compositional representation of parametric optimization problems with symbolic variables and constraints that are inspired by constraint optimization tools such as Casadi or CVXPy. On our backend, we are using modular and imperative object-oriented construction of dynamic computational graphs with GPU-accelerated tensor operations provided by Pytorch. So here we are really combining the benefits of both worlds. Symbolic formulation of high-level abstract problems from optimization community that is being parsed to back-end solver, which in our case is GPU-accelerated autograd from Pytorch. So why are we developing NeuroMANCER? First, there is no unifying scientific machine learning framework in Python that would combine constraint optimization, optimal control, and dynamic systems in one unifying toolkit. And our objective, our mission is to deploy this unification in Python. We are heavily influenced by deep learning and autograd tools, primarily by Pytorch as our main dependency. We are also influenced by the Julia scientific machine learning ecosystem. Our front-end user interface is inspired by constraint optimization and optimal control tools such as Casadi, CVXPy, Pyom, or Jump in Julia. Our problem formulations is inspired by parametric programming, where current tools are only available in MATLAB, such as YAML or multi-parametric programming toolbox. And we combine everything together based on modern control theory that includes model-operated control, reinforcement learning, dynamic systems theory based on differential equations, and constraint optimization theory based on Lagrangian methods, optimality conditions, and iterative solvers. So once we have this unifying scientific machine learning library, well, what can you do? Well, scientific machine learning library allows you to combine systematically scientific computing methods like ordinary and differential equation solvers with modern machine learning such as deep learning architectures. The workhorse of scientific machine learning is differentiable programming. That is a paradigm in which numerical computer programs can be differentiated via automatic differentiation. Here, we have been selecting only few papers that we have been encountering and have been influential in shaping our framework. Foundational papers such as differentiable programming by the Julia community, physics-informed neural networks, neural differential equations, universal differential equations, Platorao's papers on differentiable optimization that come under different names such as convex optimization layers, of learning with hard constraints, deep declarative networks, end-to-end constraint optimization, and differentiable control problems such as differentiable molecularity control. We want to have one unifying framework that allows you to have a library of all these different methods. You can combine them in arbitrary way, construct complex computational graphs to tackle your specific domain problems. So what can NeuroMANCER do for you in this quest? Let's say you have some specific domain problem, you have its mathematical formulation that can be given as a constraint optimal control problem, parameterized by, let's say, your operating conditions or different price signals or different user preferences. And you want to solve this over the distribution of the scenarios. Provide you with a minimalistic user interface that is based on symbolic representation of your problem, where the variable is the main class representing the symbolic quantities. It can be temperature, can be price, it can be pressure, it can be distance, acceleration, or any abstract variable that helps to formulate your problem. We are also providing you with a library of standard deep learning architectures, multi-layer perceptrons, recurrent networks, graph neural networks that can be wrapped in our map. And instead of having a tensor-based neural network, now we are having symbolic wrapper on our neural network that is allowing you to combine different variables in a complex computational graph. We are also providing you with inline operator overload-based interface that allows you to represent arbitrary algebraic expressions, that also works with Pytorch built-in functions to construct new composite variables that now you can use in defining your objective terms by directly calling minimize method on them, using comparator operators to directly instantiate inequality and equality constraints. And now you can combine them all together in different differentiable loss functions, such as penalty-based methods, Lagrangian or barrier methods, that allow you to have one differentiable loss can be backpropagated through a computational graph in one aggregated problem, which you can visualize as a computational graph. So in the forward pass, you have a data set that is being propagated through your differentiable components, like neural network architectures. You evaluate a set of constraints and objectives, aggregate them in loss function, and call backward pass to compute the sensitivities of unknown parameters that you want to train given the parametric scenarios. After you train, you can visualize your solution for constraint optimization problems, system identification of dynamic systems, or optimal control problem. So how do you start using it? Let's take a look on our installation requirements. You can find complete documentation on our GitHub webpage that comes in the PDF form that introduces NeuroMANCER and all the algorithms behind it or the architecture. It can also come in an online form based on our doc strings, where you can find the source code and function signatures and definitions of each of our base classes. You can also see the minimum working example of NeuroMANCER syntax. And the complete installation is also found in the README. We are based on 3 libraries, core library NeuroMANCER and 2 subsidiary libraries, SLIM and PSL, where SLIM stands for structured linear maps that are essentially drop-in replacement for Pytorch and then linear module for stable learning and inductive priors for low-level physics information learning. We developed more than 20 linear algebra factorization and regularization that allow you to learn symmetric matrices, sparse matrices, positive definite matrices, matrices with bounded eigenvalues and singular values that can introduce powerful and useful inductive biases in your deep learning architecture. Second library is a small Python system library that comes with a set of ordinary differential equations that are simulated by SciPy package to provide you with trajectories for benchmarking your dynamic system and optimal control problems. Once you cloned all the libraries, you can install our NeuroMANCER environment in the conda install. For Ubuntu and Windows user, we are providing with 2 YML files. If this doesn't work for you or you are a Mac user, you follow these steps for the general installation and you install all the dependencies. This should take only a few minutes. And after you have installed the NeuroMANCER environment, you install the NeuroMANCER ecosystem by running the Python setup of each of our libraries so you can import modules from them. Some of our examples are dependent on third-party libraries such as CVXPy or Casadi that are not contributing to the core NeuroMANCER library but are necessary for benchmarking. For further information about NeuroMANCER, you can read our scientific papers and reach out to us with questions. So in the end, who is behind the NeuroMANCER? I want to acknowledge the active development of our core team composed of Aaron Tuor, James Koch, Stefan Dernbach, and our scientific lead Draguna Vrabie, and our former contributors Mia Skomski, Zhao, Chen, and Christian Legaard. And of course, the generous funding from US Department of Energy and Pacific Northwest National Laboratory, which allows us to conduct this work. Thank you very much for spending time with me and see you at the next tutorial.